share my screen and come over here. And we have a couple of announcements to get started with for today. And then we'll get into some talking about a lot of homework assignments this week. And very likely this will be the last week that we'll be meeting in person because my wife's due date is beginning of next week. Yeah, thank you. Yes, we hold the applause until the baby comes. So announcements first. So reminder that you'll have your last quiz on Wednesday this week, and it'll be about the glob. And there's going to be a lot of very tricky questions on the quiz. I intend to make it the hardest quiz that we've had because it is a topic that I continue after 20 years of using the glob, continue screwing up and having relatively disastrous consequences with it. So the most semesters actually, and I lucked out this semester, but most semesters at some point I do something really stupid with the glob and end up bringing down the Lambda server. It didn't happen this semester, but this is one of my favorite stories in computer science, history of computer science, that I want us to talk about real quick. So it turns out that the engineers at Pixar accidentally deleted all of Toy Story 2 while they were working on it because somebody used the glob incorrectly. And there's this fairly detailed story here that I would encourage you all to read through about what happened, but I'll go through the highlights here. I don't know if I've done this actually before in Firefox, but I forgot to scroll to the right spot here. And we all know that from our usage in Vim that programmers use the slash key to search. And Firefox is a web browser developed for programmers. And so you can search in Firefox by pressing the slash key, and that brings that up down here. And if I type in rm, there we go. So here is the particular command that ended up getting run by somebody. You can see the glob in there, the rm command. And this was in 1998. People were working on it. This anonymous person, they still don't know who ran this command, ran it. And at the time, everybody at Pixar had access to read and write access to every file on the system. And this person was working on their just like one particular animation, thought that they needed to delete something, and so they ran this command, and they did delete their animation, but the command ended up taking an hour or so to run. And the other animators just suddenly noticed that the characters were disappearing from their renderings. They actually have a picture down here of here's Woody with Jesse right here, and Jesse's whole body has been deleted at this point while they're rendering. And yeah, it turned out also that at the time, Pixar did not have a good backup system for their data. It's common for backups to use something called tape drives. It looks like VHS, but it's storing like actual like bits and bytes on these tape drives, and there was a problem with their backup system. And so after like an hour after this command had run, everybody was in total panic mode because the entirety, like 90% of Toy Story, had been deleted before they managed to unplug the computer. And they didn't have any backups to get Toy Story back. Fortunately for them, it turned out that one of the animators had taken a paternity leave and had illegally stolen the copy of Toy Story and was working on it from home against the law. And but they were able to recover most of Toy Story from that accidental backup that somebody had on their laptop. And so now my kids get to watch Toy Story. And that should be a reminder that anytime you're using the glob command, it'll be a powerful thing to use, make things like very convenient, but sometimes it's, so we call it in the computer science world, we call this a foot gun because it is really easy to shoot yourself in the foot with it. So yes, motivation for the glob quiz, do well on that. And one of the reasons that I'm emphasizing all of these weird edge cases of the glob up front is so that you get into good habits of working with these dangerous tools so that hopefully you are not the cause of potentially destroying a company by running it. Yes. Question is, why don't they put more guardrails on the glob? And the answer is that um, uh, there are actual um, I mean, it's sort of like if you're working at inside of a kitchen and people are using knives everywhere in a kitchen, why don't they have more guards on the knives? It's because, like, sure, somebody could come in and start stabbing everybody, but it's expected that chefs know how to use a knife, and it's expected that programmers know how to use a glob, and all of these other things that are dangerous. Um, so yeah, this bash shell is the default shell that we're using in the interactive terminal. This was first written in the late 80s, 1989, and hasn't been significantly changed since then. And so back at the time when it was first being written, people didn't know about all these like weird edge cases. And now for backwards compatibility reasons, it has to stay how it is or systems will go down. There are newer shells that have slightly different behavior that are intended to be more safe, but nobody uses them because they're not backwards compatible. So you can't just like go onto the Lambda server and use the script or expect that a script that was written today will continue running 30 years from now, like the current shell scripts have been running for over 30 years. Yeah, good question. But yeah, no guardrails on most of the things that we do. Any other questions so far? Okay, I've posted your next 2 assignments in this class. For those of you graduating this semester, these will be the last 2 assignments that you'll have. They are on our topic 10 folder under the MapReduce section. Down here, all the way at the bottom in this homework spot right here. There's a link to the instructions right here. We'll go over that in just a second here. The due date for this, the hard deadline will be 3 weeks from now, May 2nd. This is a very hard deadline because grades are due for those of you graduating in just like 2 days after this. So the normal late policy will still apply, but at some point your grade will be due. And we'll talk about this in detail today and why there's this sort of extended deadline. There's also a new folder posted here, topic 11 graphs. This has your a programming assignment related to the Risk board game. The due date for this will be April 25th. So you have 2 weeks to work on that as well. So both of these are relatively largish assignments, so there's lots of time to work on them, but recommend not putting them off until the end. We will have a lab this week as well, and the lab will have the normal due date of the end of the week. Any questions about anything administrative? Okay. Then we're going to start today, spend most of today talking about this Twitter coronavirus assignment. We've seen all the tools that we need for it now, talking about the shell and all the your lab last week with running things in parallel. And now we'll see what we can actually do with it. If we have time, we'll start talking about the risk assignment. So this Twitter coronavirus repository here. And again, we're going to be measuring or monitoring the spread of coronavirus on social media throughout the entirety of the year 2020. And so we'll be working with this large scale data set. We've seen before that it's almost 4 terabytes in size. This data set is multilingual. You're going to be having to do things with not just English language tweets, but every language here in this assignment. and we'll be introducing this idea of MapReduce, a very popular paradigm for large-scale computing. This is a good sort of thing to put on your resumes, applying for internships or job. This is like a key buzzword. And the overall structure of this assignment is something that you'll be able to, or the goal of it is something that you'll be able to like show to future employers about, look at the cool things that I can do and make them want to hire you. So background, again, this about the data section right here, things that you've already seen so far about just where the data is stored on the Lambda server, the formats of the zip files. So you can use this as a reference, but you've pretty much seen all this material and these commands down here. The first new thing here is this MapReduce procedure. So we'll talk about what that is and then about the assignment. This picture right here is sort of the high-level description of what's going on in MapReduce. MapReduce was made famous by Google in 2004. They released a system for doing MapReduce that previously, when people were doing large-scale computing systems, they used specialized, expensive computers for the task. And Google said those specialized computers are too expensive. We can do it with just ordinary hardware. And they invented this MapReduce paradigm. So it's been around for about 20 years now, but it's still sort of the number one tool that people reach for large scale computing. It's divided up into 3 steps here. This first step is sort of trivial, so it doesn't even get a mention in the name here, this partitioning step. Somehow, if we have a really large data set, so I've represented this in this picture by this like long strand of DNA, we have to break this up into smaller data sets that we'll be talking about or processing individually. And for our data set, this is already done for us already. You've seen there's the individual zip files for each day. And so that's what the partition step is, just somehow dividing up your data set into smaller chunks. So that step's already done for us. The more complicated step here will be the mapping and the reducing step. And usually the reduce step is somehow like really easy to do, and all the work really is done in the map step. Like 80% of the coding or work that you have to do is in this map step. And what we do in the map step is we'll somehow summarize each of these smaller data sets independently into, I've just drawn this as a black box because the exactly what we're computing can change from problem to problem. So we don't need to know the details here. All that we know is that there's just some function that takes a small data set into a black box. And then in the reduce step, we have some way of combining these black boxes together. And then that will combine them all into a single black box, a single result that's like the result of doing our computation over the entire data set. It turns out there's some really interesting math that goes on behind the scenes that makes all of this work, but we'll be focusing just on the coding stuff and less on the math. Runtime analysis, real quick. The stuff that I'll talk about in this section here is really like when people like me think of computer science, when computer scientists think of computer science, this is the sort of thing that we're thinking about, talking about runtimes of these high-level algorithms, not even looking at code, and like what sort of in principle is possible. So here we're going to have these 2 variables. The text on the screen is, I don't know, I apologize that it's sort of in paragraph form, but that's so that you can reference it later easily. But there's 2 variables. Here is n is the size of our data set, and p is the number of processors that we have. So for our data set, this n is trillions, because we have trillions of tweets. And then this p is 80, because we have 80 processors, 80 CPUs on the Lambda server. And the ordinary time to do one of the typical data analysis is linear in the size of your data set, this O of n right here. But with the MapReduce procedure, what the runtime becomes is this formula right here of O of n divided by p plus the log p factor over here. The p is always much, much smaller, or typically much, much smaller than the n. So we get this factor over here of O of n divided by p. In this case, we all have 80 processors, and so we'll get an 80-fold speed up by using this MapReduce system. That's the basic summary of this runtime analysis. There are more like complicated runtimes of MapReduce. These sort of other paragraphs down here go into a little bit about more complicated runtimes. Recommend reading through it, but you're not going to be quizzed or tested on it. So it's not imperative that you fully understand this stuff. But again, upper division CS courses, we more talk or we don't talk about programming stuff. Instead, we talk just like in principle about what's possible. So this sort of runtime section is intended to get you more of a sense about what an upper division CS class is like. Okay, so the actual tasks that you'll have to complete for this assignment, they're divided up into two sections, this background tasks up here and the programming tasks down here. The background tasks involve things that are not coding things that you have to implement, but just getting you familiar with the setup of the repository. So things like forking the repo. And then I've given you some files, a map.py file, a reduce.py, and a visualize.py. And these tasks up here are just getting you the background for running those files. In the past, so this week, this lab that we had this last week, you were using things like the unzip and the grep command to analyze an individual zip file. If we take a look here for a second at so in this src or source folder is where the map.py file is. If we take a look for a second about the size of it, you can see it's got, I don't know, so 77 lines of code right here. This, as it's written right now, is doing just the things that you have were previously doing just in bash. So that like one-line bash command is equivalent to these 77 lines of Python code right here. But you're going to have to modify this code right here so that it's keeping track of how many times these different hashtags right here are mentioned inside of different countries. Right now it's talking about, or it's keeping track of which languages are using the different hashtags. You'll have to modify this code so that it's keeping track of which countries are using the different hashtags. In order to do that, the locations that you'll have to be writing the code for are in this inner for loop right here. There's a big outer set of for loops and things that are just opening the data sets so that you can process it one line at a time. And then eventually inside here is where you'll get access to each tweet one at a time. And so this is the place where you'll be modifying your code. In order to figure out how to modify your code, you're going to need to actually take a look at the JSON object that stores the tweet information. I'm not going to show you exactly where the country information is stored in there. You'll have to figure that out for yourself. It'll also be the case that some tweets won't have that information, and so you'll have to figure out how to deal with that. The easiest way to do that, my recommended approach, is using try and except blocks around code that you put right here. Where did I? There it is. But so in the background tasks, just running this, eventually later you will be modifying it. The visualize.py file at the current point in time, all it does is print some things to the screen. And so this will give you some familiarity with how to print those things to the screen. And then this reduce.py file, you won't have to write the code that merges things together. It's already written for you. Your only things that you'll be editing are in the map.py file. This will just show you how to be running that reduce to combine things together. And then you can visualize things. The important thing here is that you'll be able to visualize both on the output of the map.py, so visualizing the output of a single day, and the output of reduce.py here is the output of all of your days together. You'll be able to run the same visualized code on both of those outputs here. So that's the main point of this this background task, just getting you the familiarity with how to run the things in the terminal, so that when you come down here to the actual programming tasks, there you're not going to be confused about the terminal. It'll just be do stuff in Python. I realize this is all a little bit abstract so far, but any questions so far? Okay. In the programming tasks, so you'll have to modify that map.py file. There's this hint down here about how to do that. This is, for most students, will be the hardest part of the program. The key hint that I have for you here is that when you're doing the debugging of this map.py, only run it on a single day at a time. It's tempting to try to run it on everything at once, but only run your map.py on a single day at a time until you're 100% sure that it works. And then you can run it on everything together in this task one right here. You'll have to create a shell script, run maps.sh, that uses the no hup and the ampersand to make everything run in the background for you. And this is going to be the main like computationally expensive part of this assignment. Anytime you're doing map reduce, the reduce steps, the partition or visualizing anything that you're doing before or after the map, those will all be very, very fast. It's the map step that is slow, and that is what you'll need to make sure that you have enough time, computation time to do this. In the worst case scenario, it can take up to a week for your run maps.sh to complete running. The worst case scenario, meaning everybody all starts your run maps.sh at the same time together, then there'll be a lot of contention for the resources on the Lambda server, and it'll take about a week to make this run. So in the due date for this assignment, I mentioned that it's May 2nd, but I recommend that you try to have everything working by April 25th, a week before, just to ensure that you have the computation time to do that. Every semester that I have this project, there's always a handful of students who, the day or two before the assignments actually due, they're running their code and it's not finishing, and they're always asking for extensions, and the answer is always no. That you don't get an extension for the computation not finishing in time. So this will be the main part that takes a long time to run. After you've completed this task here, there's a little bit more coding work to do, but the bottleneck there will just be your ability, how fast you can code. There's two plots that you'll have to generate for this assignment, a bar plot and a line plot. The tasks here, task 3 and 4 down here, describe like what those should look like. I'm intentionally not giving you examples of what those plots look like, and I'm intentionally not giving you any sample code on how to create plots if you've never done that before in Python. In this case, you'll have to, I have links to the documentation that you can look at over here, but I want you to get familiar with just reading these sorts of documentation about libraries that you've not used before and plugging them into a bigger project and figuring out how to use them. So happy to talk about you, or at least this week I'll be available to talk about if you have questions doing that, but I want you to try to do as much of that on your own as you can. The submission for this assignment, you'll be so forking this repository, but then you're going to 100% delete the entire contents of this README file, and you'll create your own README file that has all of the plots that you create and an explanation on it. And the intent of this README file is to be something that, like, in your applications to jobs, if they're asking for sample work, that you could give them this link to the repository and show it to them, and you'll have a cool project with fun pictures and explanations on it. So there's not like intent, or I don't have a specific format of what your README should look like, but it should be something that you would want to show to a future employer. I've had a handful of students tell me they've shown it to future employers. I've had one student say they specifically got the job from this project. Then, so grading for this, 32 points. There are no like concrete test cases for this assignment. There's a detailed reason down here if you're wanting to read that, but the high level takeaway is that these large scale data problems in general, hard to create test cases for because you can't upload 4 TB of data to GitHub Actions in order to run test cases. And so whenever I'm seeing other people who have like run a large scale data analysis, I know they don't have test cases for the things that they're doing. And so I'm always skeptical about, is their code like actually correct? And so you should be also a little bit skeptical of your own code. Is it actually correct? And because you don't have these test cases telling you that it's safe to progress on to the next task. And so make sure to be very careful. Don't go on to the next stack until you're really sure that your previous task was complete. Again, so 32 points, 8 points just for the actual like Python code if it looks reasonable in your map program, and then your shell code in the reduce. Your README repo, 8 points, and then the different plots that you get, each of those sections worth 8 points as well. The most common ways people miss points are if you have incorrect data plotted, then you'll miss points both in the section 1 up here from the code that's generating the data, but also miss points in the plot itself for not having the right data. So you can lose a lot of points this way if your map program's not working correctly. A little more subtle, or yeah, I guess subtle is the right word. If your plots are illegible somehow or not what I would consider reasonably formatted, then you'll lose points for that. So I think I'm pretty generous on what it means to be reasonably formatted, that I just don't want to have like, I don't know, I have to be able to read it, have to actually see what's going on. But there's always quibbling where students thought they had a reasonable plot, and I disagree. So easy to lose points here. Any questions about anything on the project? Yes. Question is, how does the late penalty apply to this rubric right here? You do not lose. The late penalty does not apply to each thing here individually. The late penalty applies to the 32 overall. So if it's 1 day late, it's only 1 point off. Yeah, good question. Any other? Yes. Question is, can you collaborate on this project? The answer is yes. The heap last homework assignment is the only thing that had the collaboration limitation on it. Definitely recommend everybody working together in QCL and trying to get stuff working for this project together. So collaboration allowed. Any questions? Yes. Question is, how much time does this project take? I would say allocate 1 week of just letting the code run. So that's not a week of like you thinking about it, just you hit enter, and make sure you have a week between when you hit enter to run everything and the due date. And then in terms of the actual code itself, it took me probably 2 hours to create the whole assignment from scratch. So I don't know what that translates into for students. I think this is, I think the code itself is easier than the AVL tree. There's not like any particularly hard debugging things going on. So it's easier than that. I think it's easier than all the container assignments, just one segment at a time. The hard part of this assignment is just there's a lot of things going on, and it's relatively open-ended without these test cases to guide you. So if you feel like you really leaned on the test cases for guidance in the previous assignments, then expect this one to take longer. If you feel like you like the more open-ended things, then maybe the same amount of time as a typical assignment. Good questions. Any other questions? Okay. We're going to spend the rest of our time today in class then talking about this topic 11 folder right here on graphs. And graphs, a nice Toy Story meme here, are everywhere in computer science. Well, they're one of the key strategies that we have for creating algorithms is to somehow describe that algorithm as a graph problem. And we'll talk about what that means here in a second, and then use an appropriate graph algorithm. Some quick high-level examples here are something called GoFi, or good old-fashioned artificial intelligence. Every video game that you've played, for example, has good old-fashioned artificial intelligence in its back end. Even inside of a lot of data analysis, there's a lot of these GoFi algorithms that are going on, and these are all based on graph algorithms. We've seen a handful of the sort of classic software engineering interviews, questions in class. Those are sort of like the LEET code questions. Basically, everything that's not covered in this class, in the data structures class, is somehow related to graphs. And I've plugged this course a number of times before, but if you go on, after a great follow-on course for this course is CS 148, taught by Professor Cannon. And that graph algorithms course is going to really build off of, I mean, everything in this class, but really this last set of material on graphs here. And that's the other main, probably like 80% of software engineering LEET code questions come from that graph algorithms class, the other 20% from this class. Okay, in order to talk about graphs, we're going to, I have two handouts here, a handout of a risk board and a handout of a bunch of words connected together here. And we'll talk about what graphs mean on these two problem domains. There's a bunch of vocabulary that we'll be going over. Again, you don't need to know exactly the definitions of any of these vocabulary terms, but I will be using them all throughout today, and they're used in your next homework assignment. You'll have to just understand what they mean in context. There's also three particular algorithms that we'll need to know for this class: depth first search, breadth first search, and something called Dijkstra's algorithm. If you recall, maybe a month and a half ago, I had a picture of Dijkstra saying that object-oriented programming is such a bad idea, could only be invented in California. This is that Dijkstra guy. And this algorithm right here is probably the most famous algorithm in computer science. You'll be implementing this several times in your risk homework assignments. The textbook for all of this is chapter 8 over here. There's a lot of graph problems inside of here that we're not going to cover at all. The main ones that you'll want to think about are the breadth first search and the Dijkstra's algorithm down here. The other ones we won't need, and there's no code that is useful in this chapter. So if you're referencing the chapter, referencing the textbook, it would only be for the high-level ideas. There's no code at all that would be useful here. Okay, let's start by talking about the risk board game and your risk homework assignments. So if you've seen the game of Risk before, this is what the board looks like. It's a map of the world. Each one of these territories over here is one section that players can control, and you can move armies from one territory to another by attacking other territories. Many board games have this sort of setup where you have different like squares or territories or countries, and they're somehow connected to each other. And the common way that we represent all of this information is as a graph. We'll come over here and we'll take a look at what that graph actually looks like. So this image that I have is still that same still that same board here, but now I've drawn lines between each of these territories, and those lines indicate which territories are connected to other territories. Actually, before I go over this too, I should just highlight for those watching online that this image, under the images folder, the two PDF files right here, words.pdf, and let's go to the master branch. Words.pdf and this board3.pdf. Those are the printouts that we're going over right now. This is the board3.pdf file. This in the computer science world, a graph is something that has nodes. Each of these circles is a node, sometimes called a vertex, a node, or a vertex. And then the lines connecting between those nodes and vertices are called edges. And in this particular problem, the way we're modeling this problem is that every territory is a node in our graph, and two territories have an edge between them if they are adjacent to each other on the map over here. And so this lets me take any map, no matter what the structure is, and model it in a common framework using graphs, and then apply these standard graph algorithms. Another term that we'll need here is what's called a path, and a path is a collection of edges. Path is a collection of edges. And in order for a path to be valid, that collection of edges has to, they all have to be touching each other. So this is a relatively intuitive idea here. And in the board game of Risk, we're often needing to know what is the shortest path between two territories or two regions. And here I have a node down here in Argentina that has a 500 on side of it, and inside of it right here. This 500 in the Risk terminology, or the semantics from Risk, this 500 is the total number of armies that I have right here. That 500 right here is the total number of armies in Argentina down here. There's another 500 armies up here in Brazil, and so on. Each of these numbers are the number of armies that the player has on that particular territory. And then the color indicates which player owns that territory. So in this game right here, we just have two players, a red player and a blue player. And the blue player seems to be winning because they own most of the world. Whoever conquers the world first is going to win the game of Risk. In terms of graph terminology, these numbers right here are called weights of the nodes. So the number of armies that I have on each territory here is the weight of the node that corresponds to that territory. Any questions about any of that so far? Okay. Then we're going to pause our discussion of Risk here, and we'll take a look at another problem for a second, and then we'll come back here later on to Risk and run some algorithms actually on this board here. So the other graph here is this words.pdf file, and in this case, we have a bunch of words. Each word is a node. So this is a node right here. And two nodes have an edge between them. Two nodes are adjacent if the corresponding words share or differ by at most one letter. I'll write that at the bottom. Two words are adjacent, meaning they have an edge between them. if they differ by exactly one letter. And in this problem here, if well, this should be reminding you of the word ladder problem that we did a long time ago. But it turns out the word ladder problem, if you frame it as a graph structure in this way, then we can use graph algorithms to solve it rather than the sort of stack queue pseudocode that we had before. And so we're going to introduce an algorithm called the breadth first search algorithm to see exactly how that works. So our algorithm here will be breadth first search, often abbreviated BFS. And we'll step through the breadth first search on this algorithm, see how it compares to the word ladder problem. Again, the BFS here is the breadth first search corresponding to breadth first search right here. Well, yeah, we're going to look at all of these algorithms here, the depth first search, the breadth first search, and Dijkstra's algorithm here. We're going to look at them just intuitively at a high level, understanding what they're doing in pictures, and then we will take a look at pseudocode corresponding to each of these algorithms. The pseudocode by itself, kind of difficult to understand, similar to how the pseudocode for the word ladder was difficult to understand. But I think the pictures, walking through what the pictures are doing, you'll find will help understand the pseudocode better. So in this case, what we're going to do, the example that we're going to try to do is we're going to start with this node over here, slick. And our goal is going to be to find what is the shortest word ladder from the word slick over here to the word stone over here. And we'll use that, or we will compute that using this breadth first search algorithm. Yeah, so I gave you the printouts to give you, so you don't have to copy down this graph, but you can sort of draw the highlights of this algorithm on this piece of paper to just keep track of what we're doing here to follow along. This slick word, again, is our start word. And the very first thing that we're going to do in a breadth first search is we're going to compute all of the neighbors of our start word. So in this case, there's only two neighbors here, this word slack and this word stick. And so I'm going to draw a new sort of circle around slack here and slick and stick like that. And now this red circle here contains all the words that are distance 1 away from our start word. So this is distance 1 here. Everything in red is distance 1 away from our green here. And our green here is like distance 0 away from itself. We're going to iterate this sort of procedure several times where we're computing all of the things that are a certain distance away from the start word that we have over here, this word slick, until we find this word stone. And at each one of these iterations, one of the sort of key vocabulary words that we'll see is this word frontier. And here the word frontier always refers to, it's basically what this line is selecting. So the frontier at distance 1 is this red line right here. I'll put that in red again. The frontier at distance 1 contains this word slack and this word stick inside of it, but does not, for example, contain this word smack because smack is not distance 1 away from the word slick. At each iteration of the breadth first search algorithm, in order to go from a frontier of distance 1 to a frontier of distance 2, for example, in order to go from distance I to I plus 1 more generally, you have to just find all of the neighbors of everything in the frontier and create a new frontier with those neighbors. So here we have slack is in our frontier. Let's find all of the neighbors of slack. So black up here, that'll be in my new frontier. Then smack is next to slack, shack is next to slack, snack is next to shack, all three of those words, add them in. Um, let's see, so stack and shuck are not next to slack and not next to anything else, so those do not get added in. If we look at this word over here, this word stick, that's next to stink, not next to stunk, but it is next to stuck, not next to shuck. And so now this sort of green line right here, this is my frontier of words that are distance 2 away from my start of my breadth first search over here. So this is the distance 2 frontier right here. You'll notice that this word shack, for example, has some paths that we can take to get to it that are bigger than distance 2. So the distance 2 path would be slick to slack, then taking this path over here to shack. But there are larger paths, like going from slick to slack, then to smack to shack. That would be a length 3 path. Doesn't matter that there are some paths that are longer. The only thing that matters is that the shortest path over to this word here is distance 2. And so that is, so it gets into the frontier for distance 2. We'll complete this here in a second. Any questions so far? Yes. Question is, shouldn't stack right here? Oh, yeah, so slack up here. I missed this line coming down over here to stack. And so, yes, this, let's cross out all of that stuff and add in stack like that. Good observation. Thank you. Other questions? Is it seeming relatively straightforward so far? What to do? What is question? Question is, why is shuck right here? So shuck, my intention here is that shuck is not contained in the frontier. That the squiggly line includes stink, excludes stunk, includes stunk, excludes shuck, includes all of these. Yeah. Okay. And now we're going on to our distance 3 frontier. So we take everything in the distance 2 frontier right here, and we'll find what are its neighbors. So here, now we'll include shuck as a neighbor of stuck, stunk here as a neighbor, stank, and shark. I believe those are the only neighbors there, and that divides our distance 3 frontier right here. And then our distance 4 here, so all of the neighbors of things in distance 3. Shank, I am apparently very bad at drawing my lines. This time I will undo to get, yes, you're right, shank should also be there. There we go. So that's distance 3. And now on to the distance 4 frontier here. Here, so things next to the things in blue. So stark right here inside of blue, share over here next to shark, and then shave and shove, not next to anything, shown next to shank. Hopefully I got that one correct. Distance 4. And now when we get to our distance 5 frontier, things next to distance 4, our target word here, stone, is next to it, so we will include that. And then shove, shave, shame, stare, all of those inside. So at this point, we've gone a pretty far ways, and we finally encountered our word over here that we're looking for. This tells us so far that the length of our shortest path, to go from our origin, our start word, over to our target word. The length of that is 5. In order to actually get to the target word, what we have to do is backtrack, go backwards from this target word back to the origin. And here, so if we start at stone, the way to go from the 5 to the 4 is by following this path right here, taking me to shown. And then the way to go from shown in the distance 4 frontier down to the distance 3 frontier, following this right here to shank. And then shank over here has to take us to shack over there. Shack will take us up to slack up there, and then slack finally taking us back to slick over here. And this, following this orange path right here, this orange set of edges, is our word ladder between slick and stone over here. Any questions about? Yes. The distance 0 right here is like starting at slick and ending at slick. So slick is distance 0 from itself. Good question. Any other questions so far? Okay. So what we're going to do next is we're going to see how the pseudocode for our word ladder assignment relates to this breadth first search algorithm. If we come over to the risk assignment here, so I'm in the risk repository, and scroll down a little ways. Here, it's giving us the pseudocode down here for the breadth first search algorithm for shortest paths. And the particular algorithm that is presented here is with the language of the risk territory of the risk game instead of the language of the word ladder game. But it's exactly the same pseudocode that you had before, except wherever the word word was used, I've replaced that with the word territory. Wherever the word dictionary was used, I've replaced that with the word board. Your thing that you'll have to implement for the risk assignment when you do the there'll be a shortest path function that you'll have to implement on the risk board. The implementation for that will look basically exactly like the code that you used for the word ladder assignment. In this case, the key data structure for this algorithm is the queue that, and we'll see here in a second how this queue data structure relates to the frontier that we were talking about in the image. The other algorithms, right here, these other graph algorithms, depth first search or Dijkstra's algorithm, their key data structure is a stack for depth first search and a priority queue for Dijkstra's algorithm. So again, the priority queue is another word for the heap, the thing that you implemented in the last assignment. And it turns out that by just substituting the queue for these other data structures in the pseudocode up here, this is the one with the pseudocode. Turns out just by substituting, instead of creating a queue here, you created a stack, you would get depth first search, and instead of using a queue here, you used a heap, you would get Dijkstra's algorithm. So all of the code that you'll be writing is going to be, you'll be implementing all these algorithms. They'll all be very, very similar to each other, just with different data structures doing different, causing the algorithm to behave in a different way. So what we're going to do next is we'll take a look at why exactly, like what exactly is special about a queue here. How does it relate to the breadth first search that we we're just talking about in pictures? And then we will, if we have time today, we'll talk about the heap and how that relates to Dijkstra's algorithm. And we'll do that specifically with the risk example. Maybe, so before I relate the queue to the picture discussion that we were having up here. Any questions so far? Okay. So here, well, let's just remind ourselves for a second, what are we doing with our queue? That here this stack was supposed to be like the word ladder itself. So the stack corresponds to the path that we're creating. The stack corresponds to this orange line over here of the connections of words or connections of nodes to each other. And the queue is how we determine which node to investigate next. The queue is going to be tracking our frontier and what word we're going to look at next. So every time where you see like the frontier, where we switch from like distance 1 to distance 2, that's related to the queue. The reason it's related to the queue is that at every iteration of our for loop or of our while loop down here, when we do for each word in the dictionary, for each vertex in the graph, for each territory on the board, we're going to add that to the queue. And so here, starting at our neighbors, we add all of our neighbors into the queue. So at slick here, our neighbors of slick are stick and slack. So when we're looking at this node right here, I'm going to draw in blue for all of these nodes what the current status of the queue looks like. After processing the slick node, our queue will start with slack on top and then stick on the bottom. The reason for that is because these two words right here are the neighbors of slick. And then when I'm going to decide what node to process next, I'm going to take something off the top of the queue, the thing that was most or least recently, most distant in the past, inserted into the queue. In this case, they're both inserted at the same time, so it doesn't really matter. If I look at slack next up here, then we would take slack off of the queue, and our queue starts with just stick on top. So at this point, before we've processed slack right here, our queue starts with just stick at the top. And then we add all of the neighbors of slack onto the queue. So here, slack has a lot of neighbors. So it has black, smack, shack, snack, stack. All of those get added onto the queue. Stick, black, smack, snack, and I won't write them all out. But all of these neighbors right here got added onto the queue. The key thing about the queue, though, is that we're not going to look at these neighbors. We're not going to look at the things in the frontier of distance 1 until we've processed this stick up here. And because the stick was added before everything in the distance 1 frontier, it's guaranteed to get processed first. So we're guaranteed to process everything in the distance 0 or the distance 1 frontier here, the red frontier. We're guaranteed to process that before processing anything in the distance 2 frontier. So stick up here is in the 1. All these others are in 2. And because we're using a queue, we'll process stick before we process these other ones. So down here, processing stick, take that off the queue, and then it's just black, all of the neighbors of slack over here, and then all the neighbors of stick. And this is the last word that was in the queue here, added at distance 0. So it's the last word in the queue that's at distance 1. And so everything that we see after that is at distance 2 in the queue. I realize that's a little bit messy of a picture here, and so there's a lot to keep track of here with what's inside of the queue. But the key thing here is because the order of the queue, we take the oldest things first. We're guaranteed to take whatever is inside of our frontier 1 before we go on to the frontier 2. And then we're guaranteed to consider everything in frontier 2 before we go on to the things in the frontier 3. Any questions about that? No? Yeah. So what the question is, what is exactly the queue like here at Stick? And the answer is that I ran out of space, so I didn't fully write it. Where can I get this? The queue contains everything that was in the queue up here. So black, and then smack, whatever was in the queue previously, and then adding the neighbors down here of stuck and stink. So at this point, this was the last thing in the frontier at distance one. And so everything that is in the queue right now is stuff that is in the frontier at distance two that we will process next. At the end, at the very last iteration of processing something in a frontier, everything, the contents of a queue will be whatever is in the next version of the frontier. So at this point, we've finished with the frontier distance one. The contents of the queue at this point are the frontier at distance two. Then when we process all of those, once we process everything in the green, the frontier will be equal to the queue. So the queue will be everything that's in the frontier at distance three, at the end of distance two. Does that help? Good question. Any other questions? Yeah. When it processes the top of the queue right here, when it processes black, what it's going to do is that it'll come up to the black. Yeah, black has no neighbors that it hasn't visited yet. And so it'll just take that off the queue and then go on to smack and start processing that. Smack similarly will have no neighbors that it hasn't processed yet. So it'll go on to snack, not process that, get to shack, and then it'll add the shark and stink to the queue. Okay, yeah, so what I'm gonna do here is we're going to go over to the risk board here. I'm gonna delete everything that I have on the screen here. We're gonna walk through Dijkstra's algorithm using a priority queue step by step the whole way, and we'll see exactly what's gonna happen here with this. In order to do this, so let's that. Close that. Let's first talk about high level, like what is the semantics of a breadth first search here, and what is the semantics of Dijkstra's algorithm in terms of our risk game board here. In this case, we're going to imagine that we're the red player down here. And for some reason, we have an objective of taking North Africa, this territory right here. There's different versions of risk where sometimes you're trying to take over the whole world, or sometimes you just take over certain countries to play a shorter game. And if you take over those countries, then you win. And so the red player, for some reason, is just trying to take this territory right here. The shortest path to doing this, just following this graph, is if we go from Argentina to Brazil to North Africa, it's only a distance of 2 away to go from here to here. The problem with that, though, for the semantics of risk, is that in risk, when you're moving your armies from one territory to another, you have to attack that territory. And this territory here has a very strong army on it, so it would be probably not a good idea to attack. We don't know if we're going to win this 500 against 500, and there might be a better route for us to take. And in this case, what we'll see is that it'll actually be more efficient for us to go from Argentina down here, coming up through North America, and then down through Europe over to Argentina. There will be fewer armies that we have to take into account, have to attack in order to do that. And even though the length of the path will be longer, what we'll call the weighted length of the path will be shorter. So in the weighted path, instead of just counting the number of nodes that you visit, you have these weights on the nodes and you count up the total number of weights throughout the whole path. And for the purposes of risk, you want to, if you're trying to get somewhere, you want to take the path that has the fewest number of armies in your way. And so you would want to use the smallest weighted path instead of the smallest path. Dijkstra's algorithm is the variant of breadth first search that uses these weights, takes them into account, and finds the shortest weighted path. So again, starting here at 500, what we're always going to have is a priority queue now. And I'll write our priority queue over here. In the priority queue, we'll keep track of our different paths and and the weights of those paths. And we'll always be able to get the most efficient path out of the priority queue. That's the special property of the priority queue, is that you can get the thing with the smallest result out very efficiently. And in this case, we will have two columns here that I'll record for us: the territory and the corresponding weight of that territory. In this case, we're going to be starting down here in Argentina, and so this is the just this pseudocode that we're walking through at a high level, but now instead of having a queue right here, it's a priority queue that's keeping track of which countries we're going to visit next. Where is, there it is. And so we're starting down here in Argentina, adding that onto our queue, and its initial weight here being 0 that we start with, because you can always go from, you don't have to do anything to go from where you are to yourself. And then we always take the top thing off of the priority queue. So we'll take that off, cross it off, and add on its neighbors. In this case, we have Peru right here for 4. Peru for 4, and then Brazil over here for 500. And then when I want to decide what my path is, I'll go ahead and draw in these lines over here about which neighbors we've considered. When I want to decide now which country I'm looking at, the sort of the equivalent of our frontier is whatever the top of our priority queue is, whatever is the country that has the smallest value in front of it over here. So in this case, Peru going to Peru has the smallest weight rather than Brazil, and so we'll consider Peru next. We'll cross off Peru from the list and add up Venezuela up here. And Venezuela, the weight of Venezuela here, this 3 will be added on to the 4, and so we get 7. That the total weight to get from Argentina up to Venezuela would be 7. And then Venezuela to Mexico, that's the next thing that we would consider. The reason for that is because Venezuela is less than Brazil over here, so we're still considering Venezuela's at 7. 7's still less than 500, so we'd still be using this Venezuela at the top of our queue, even though Brazil is right next to our starting country. Its weight is so large, it's very far away in the frontier. We're not at the 500 frontier yet, we're only at the 7 frontier. So we'll take Venezuela next, take that off of my priority queue, and add on Mexico with an 8 right here. I'm going to start switching to writing the weights over here next to the countries themselves. So here, Peru, the weight to get to Peru was a 4. The weight to get to Venezuela up here was a 7. And the weight to get to Mexico up here was an 8. Mexico still is easier to get to Mexico than to Brazil, so we'd take Mexico next. And now we have 2 neighbors over here, Eastern and Western United States. They both have a distance 9 of each other. At this point, we have two different nodes that we could consider, either Eastern United States or Western United States, and consider their neighbors. So our frontier at the level of 9 contains 2 territories. It doesn't matter, the priority queue can pick arbitrarily between these 2 territories, which one it's going to select. And so yeah, it will just arbitrarily choose the Eastern United States over here. But it doesn't matter. And here, going from Eastern United States up here to, I should remember this, I think it's Quebec, isn't it? 5 plus the 9 is the 14 to this territory, and then 9 plus 3 is 12 to this territory. And now we come back to our priority queue. The things that we have considered are everything at this point. We've still not considered the Western United States, still not considered any of the Canadian territories, still not considered Brazil. Everything inside of the red line right here are things that we've considered so far. And so the next territory we'll consider is whatever has the smallest thing that we're related that we can see to the right of this red line. The 9 is our smallest, so that's what's on our frontier right now. And so we'll go to the Western United States next. And the Western United States here connects to this territory up here for 12, and also this one over here for 12. In this case, the either path works going from Western or Eastern United States. They have the same weight right here. And so either path works. If one of them had a better path, we'd have to take our number right here. Our weight to get to this territory would be whatever is the lowest path. But both of these, either of these 2 paths now is the next thing to consider. We've considered Western US, not considered anything in Canada. Either of these 2 territories works, and so going, you just keep repeating the procedure of adding, consider whatever the territory is the smallest, and adding it to its neighbor values. So 12 here plus 2 is 14, 12 plus 2, 14, and then that is done for this territory right here. Any questions about anything? Anything so far? Is the how are people tracking? Feel like the idea is making sense? Okay. Eventually, if you keep going through this whole procedure, always taking the smallest thing out of your territory each time, you'll come up with a path over here to North Africa, and the first one that you encounter will be the shortest path over to North Africa. I definitely recommend trying to like have the intuitive understanding of these pictures and these algorithms here for working on the assignment, but in some sense you don't need to, that it can be just like the word ladder where you are exactly implementing the code that I have for you as it is. And I have, if we come down here, there is some Dijkstra specific code where I've showed you exactly what the changes have to be in order to make the priority queue work instead of just the regular queue. So the changes aren't like major changes. It's just now every time when you're adding and removing things, you have to have a formula. You have to specify what the priority is. And so making sure that those things are clearly specified in here. Actually, at the high level, that's everything for the assignment here. There's a couple of new debugging techniques that I have for you for this assignment. Instead of just doing print statements, you'll want to be using actually looking at these images, visualizing them, And so I have another video, it's already recorded. I'll upload that along with this video tonight. And that'll be all of the things that you'll need for the risk assignment to complete that. Anybody have any questions about anything? Yes. Question is, when will the risk assignment be due? You have 2 weeks to work on it. It's due 25th of April. It's a little bit larger than the other assignments because there's, I don't know, maybe it's like 10 variations on the word ladder assignment that you'll be implementing different sort of aspects of the risk algorithm. If you're familiar with the game, you have to implement like the reinforcement ability where you're only going through your own territories or only going through enemy territories for other applications. And so handful of variations. So don't put it off till the end, even though you have 2 weeks to do it. If anybody else has other questions, I'll stick around and get those answered, but that's it for